Atoms. Atoms are the smallest thing that exists, kind of. It holds the universe together like Legos, kind of. We didn't always think, oh, atoms, that makes sense. Atoms, that makes sense. No, no. Democritus, a long time ago, ancient times even, he thought, what if there were atoms? What if we cut something really tiny small? Is there something that we can't cut in half like that anymore? And so, the first atomic model was made. And it looks a little something like this. If we think of these spheres, circles, as water particles, then they're slippery, they're smooth, they slide off each other. Because water, it's not so solid, is it? Water doesn't like to be in a shape. But iron was strong, and they built a lot of stuff out of iron. So clearly, iron was tough and strong, and it had hooks that connected itself to other irons. Because that made sense at the time. Those were atoms, and my atoms don't look so cool, but that was the earliest model of an atom that we know of. This philosopher was like, this is what atoms look like. But then, this guy, John Dalton, he was like, I like this thought of atoms. And he proved atoms existed. Atoms were the smallest thingamajig in the world that built everything else, like Legos, kind of. So Dalton, he was like, all the atoms of the same element are identical. They don't look very identical in my model here, but this is all iron, again, because I said so. And then all of these particles over here, these four atoms of neon. These are all the same because they have to be. There's no explanation for why they wouldn't be completely identical and have the exact same chemical properties. But John Dalton also said that atoms cannot be created or destroyed. And that's a good thought to have. The smallest thing, why would you ever get rid of it? Why would it ever come into existence or get destroyed? Because if it got destroyed, then things wouldn't last very long. But I digress. Another guy, J.J. Thomson, he liked plum pudding. But beyond that, he had a cathode ray tube, which was a fancy-dancy piece of glass that shot light out of it. And he was like, what if I put a magnetic charge on either side? And what he found out, the light, when he shot it out, it curved over to the positive side, because clearly it was negatively charged. And that's how electrons came into existence. J.J. Thomson was like, alright Dalton, your model's cool, but mine's cooler because it's made of plum pudding. So J.J. Thomson says that Dalton's model is correct, but the whole sphere is positively charged, and there are tiny little electrons inside of it that are negatively charged. And you can take those out. You can take those out and put them somewhere else. Anyways, another guy, Ernest Rutherford. Ernest Rutherford. He liked this idea of plum pudding, but he was unsatisfied with the results from plum pudding, so he shot radiation at a very thin piece of gold. Because he hated gold. He was shooting this stuff called alpha particles, which we know now as helium nuclei. So he was shooting these alpha particles at this gold over here, and he found out that it was going straight through. And I was like, why is it going straight through? It must be empty space. There must be nothing here. If there was stuff here, it'd be reflecting off of it. So he was like, there gotta be stuff here because there's a gold sheet here. If there's a gold sheet here, there doesn't make sense. So he kept testing, and then he put this receiver block on this side. On this side. Not really. It's like this two-dimensional. I can't do it. But he did it there. And then sometimes little particles would come over here and hit this one. And he's like, wow. It can't just be empty space then. Because, well, there's something there. And also, they're getting reflected off. Stuff's coming back, which means it's hitting something. What it was hitting was the nucleus of the atom. The atom is mostly empty space, but all the mass is in one tiny piece. Like, really. But it was like, this is the nucleus of the gold. There's like one here, and then so far away the other one is. But the alpha particles are going straight by in a different direction. That was diagonal. I didn't mean to point it diagonally, but sometimes they reflect, because this alpha particle we know now as 2 protons and 2 neutrons. Those look identical. But this gold here is a lot heavier than 2. It's like nearly 200 mass units as opposed to 4. So no wonder this is going back, but it's so hard to hit because that 200 mass units is so tiny you can't hit it. Anyways, Rutherford decided that since these alpha particles are going straight through and they reflect sometimes, that must mean that there's a nucleus and the electrons aren't a part of the atom. The nucleus. There's a nucleus and the electrons are outside of it. Like that. Sort of. And that was Ernest Rutherford's nuclear model. But this guy, Niels Bohr, he came along and he was like, that's cool and all, but I'm gonna use my brain and think of a different way. So he did this experiment with light. How do I draw this? He lit up hydrogen. He plasmaed it. Hydrogen went boom. Hydrogen went bzzz. The hydrogen, it went funny, haha. I don't know how to draw this.
1 hour later.
Alright, so magically, Bohr found out that lighting up hydrogen made certain colors visible, but not every color. So it'd go like red, and then blue, and green, and yellow. And that's not the right order, but he lit up hydrogen, and some of the colors were missing when he looked at the rainbow, because it should make all the rainbow, but it doesn't. And that made him think, all right, these electrons, these fancy dancy electrons that J.J. Thomson figured out and then Rutherford put in their place, they must be quantized, which means that it's like straight values. It's like absolute, no. It's like whole numbers. When you have whole numbers, you go 0, 1, 2, 3, 4, and whatever. You don't have these fancy dancy fractions or whatever. You don't go in between 0, 1, 2, and 3, 4. Anyways, fancy dancy science team comes up. The science team of Brogle, Dirac, Heisenberg, Schrödinger. These genius man people thought up electrons are too small and too fast to visualize. So their indecisiveness decided that the electrons circling the nucleus must be a cloud. It must be a cloud because they're going too fast. These electrons, they're incomprehensible. You can't look at it. Quantum model is how it works. Because James Chadwick, man, that James Chadwick, I'm looking forward to talking about him, because I'll tell you what, James Chadwick, he discovered neutrons somehow. So James Chadwick, he looked up this atomic model and he was like, that's for lame babies. You know what? This nucleus, yeah, it's positively charged, but you know what would make it even cooler? If there were neutral charged particles inside the nucleus that gave it mass. That's why alpha particles, what we talked about earlier with Ernest Rutherford, that's why they have a mass of 4, not 2. Because 2 is just 2 protons, but 4. Also, the electrons are there, but they can't actually exist. They're a cloud. They're a cloud. Electrons are there, but they're a cloud. Just because they're quantum. Quantum model. You can't visualize it. Look at that. Quantum model. Alright, the last scientist I'm going to talk about. Maria Mayer. She's like, alright, Chadwick, cool name and all, but you know, these neutrons, you don't give them purpose. I'm going to give them purpose. And so Mayer was like, here's the shell model. Here's the nuclear shell model. It's focusing on what's happening inside the nucleus, which is shells. Like how we know that valence electrons exist or something. That's like the same thing, but inside the nucleus. So if we get rid of our really awesome idea that electrons are quantum and you can't see them at all, then we are left with this shell model. You can think about that quantized value inside the nucleus, where the protons and neutrons have a value that puts them closer or farther from the center. Anyways, Mayer decided that inside the nucleus they were organized into shells, and filled out shells mean the nucleus is more stable than without filled out shells. And when it isn't stable, it causes radioactivity and shoots out alpha particles or something. Alright, that's it. That's all I have to say. Frazzle dazzle.